let's introduce the solubility rules and also introduce what are electrolytes. All right, so a couple of vocabulary words. Again, soluble means that a substance will dissolve, which again means it's going to separate and become surrounded by solvent molecules. We talked about salts, when they dissolve, dissociate into their ions as they separate. And covalent molecules, with the exception of acids, remain intact. So we would consider when it dissolves, the final state is aqueous, AQ. And then we have insoluble, which means it will not dissolve. So if it's a salt, it remains stuck together in its crystal lattice. If it's a covalent compound, depending on its state, if it's liquid, usually you'll have a layer, so oil and water are not soluble. The less dense one will be on the top layer. If it's a solid, usually solids are more dense. So if I had chalk would be a solid that won't dissolve, it'll just fall to the bottom. Actually, that would be an ionic compound, but in a solid state, if I had maybe, I don't know, flour. Flour is kind of not a solid, it's more of a powder, but still. And the state is the same for covalents, or ionics, the state would be the same as it was in its pure state. The pure state for ionic compounds is solid. For covalents, sometimes it's solid, sometimes it's liquid. And so that's what we're going to use as our vocabulary for soluble, insoluble, the states that we talk about. And here's just a picture reminding you like what it might look like for an insoluble salt and a soluble salt. So we're going to use the solubility rules from the TRO textbook. I will supply these rules to you, although it's helpful if you kind of memorize them. Notice the way that we use this is that it's saying it's based off of the ions that we find in the salt. There's always 2 ions in the salt. So it's dependent on rules of each of them. So both of the ions that are in the particular salt matter, and the way we use this table is that you find one of the 2 ions that are in your salt that you're trying to determine if it's soluble or insoluble, and you find that on the left column. Note that on the top of the table in the left column, these are talking about if it has this ion, it's generally soluble. It would be aqueous. And on the bottom, we have ones that are generally insoluble. Now, once I've identified is it generally soluble or generally insoluble, I have to consider the other ion. So I'm going to look, what is the other ion? I'm going to go over in the same row, I'm going to go over to the second column and check, is the other ion in the exception list? If the other ion is in the exception list, it's no longer generally soluble, it would be the opposite. If I had a substance with chlorine and silver, so the chloride ion indicates that it should be soluble. However, if the other ion is silver, that would mean that it would be insoluble. If I had hydroxide ion and sodium, the hydroxide ion indicates it would normally be insoluble. However, if the other ion is sodium, then it would be soluble. So if the other ion is in the exception list, it will reverse what the generally is into the other opposite category. Also, it's let me sort of change this over so that you can see the bottom. Hang on. There we go. All right, so what you can't see on this table, it doesn't have everything listed, this one, but it is helpful to know is generally fluorides are insoluble. So chloride, bromide, iodine are generally soluble, but fluoride is in the same group as those, but they're generally insoluble. Chromates are not listed here. Chromates are generally insoluble, and except for these group 1 ions. And then silver salts are generally insoluble as well. Again, only if it's with one of these in lithium, sodium, potassium, or ammonium would it be soluble. So that will help you as well, especially on homework. On the homework, they use a different table, and they refer to it in the questions, and occasionally we get a gray area where chemists don't agree, where something on this table might say it's soluble, but something on another table might say it's insoluble. When doing the homework, you can use the check with their solubility table, but for tests and assignments in class, we will use this set of solubility rules. All right, let's just talk about some of these equations. If I were talking about this equation of dissolving. And again, I'm not really going to do this very often, but occasionally this shows up, and it does show up when we're doing net ionic equations. So the way that I would write what happens when it dissolves is going to depend on the solute. So if I add water over an arrow, so I have a solute on the left side with its natural state, and then I put an arrow and I put water above it, that's referring to I'm dissolving it in water. It's not really reacting with the water, but it's kind of like a reaction because it's changing the format of the solute. So if it's a covalent solutes do dissolve, but they do not break up. So the chemical formula remains the same, but the state will change to aqueous. So iodine is a covalent solute. Its native state, it happens to be solid. And when I put it in water, it's going to dissolve and become aqueous, but the chemical formula doesn't change. Potassium bromide is a solid substance in natural state. When I put it in water, it is an ionic compound. It's a salt. So it's going to dissociate into its ions, which are potassium ion and bromide ion. Note that the states of the ions will be aqueous, but now I'm showing them, I've dissociated them into the separate ions. If I have an acid, HBr is a strong acid. Remember, HBr, HCl, HI, HNO3, H2SO4, HClO4. So HBr is one of the strong ones. Its native state is gas. If I put it in water, it's going to dissociate 100% into H plus and Br minus ions. Again, they would be aqueous. If I have HF is not one of the strong acids. It starts with H, so it's an acid, but it's not a strong acid. It's going to partially dissociate, and this one is a little touchy, and we won't do much of it now, but if you see it, I want you to be familiar with it. It's going to form HF aqueous, and a little bit of it is going to break up and form H plus and H minus and F minus. So these double arrows indicate a little bit of it happens. So in a net ionic equation, which is coming up, if you have HF gas, it would become HF aqueous, but note that for the most part, we would leave it intact because primarily it does stay intact, kind of like these covalent. We would just write aqueous after if it's a weak acid. But if it's a strong acid, you break it up. I know that gets confusing. And then lastly, we have a strong base. It's really not different from a salt because it is a salt. So native state is solid. I put it in water. It's going to break up into its potassium ion and its hydroxide ion, which would both be aqueous state. So for this one, in net ionic equations, we're going to leave it as the aqueous state because that's the predominant form. Okay, electrolytes. So there's two different definitions for electrolytes, and one is sort of an operational definition, which is actually the more formal definition, but as far as recognizing is something an electrolyte or not, we tend to use definition 2, which is like, well, why is it an electrolyte? All right, so in substance 1, it's a substance that conducts electricity. When we're talking about solutions, and again, when we say operational definition, it's like it doesn't explain anything, but it's just if it's true, it is, if it's false, it's not. So in order to make an electrolyte, to have an electrolyte solution, the substance would have to be soluble. So that's sort of an underpinning. And then beyond that, I'm just going to put the stuff in water and see what happens. If I get very good conductance when I put the stuff in water and it dissolves, then we would call it a strong electrolyte. If I put it in water and a little bit of electricity, it conducts a little bit of electricity, but not a lot, I would call it a weak electrolyte. If I put it in water and essentially there's no conductance, I would call it a non-electrolyte. The non-electrolytes sometimes have a little bit of conductance, but for the most part, no. And so I kind of break them up into strong, weak, non. Let's talk about why it would be an electrolyte. So the second definition is any substance that forms ions in water. Now, if you remember, we have soluble salts, strong acids, strong bases would be the three that can really generate ions in water. So again, that substance has to be soluble. That's the first given. And then we're looking at if it's strong formation, a strong electrolyte would be one that all of it dissociates. So soluble ionic compounds or strong acids, strong bases. A weak electrolyte is some of it dissociates. So that would be my weak acids, weak bases. And then a non-electrolyte would be no formation. Either it's an insoluble salt or it is a covalent substance. So kind of breaking it down, if I look at a substance, I need to type. Is it soluble ionic compound? Is it insoluble ionic compound? Is it a covalent compound? Is it a strong acid? Is it a strong base? Or is it a weak acid or weak base? So once I can look at a chemical formula and type it, that will help me decide, is it going to form ions, which then helps me decide, is it a strong, weak, or non-electrolyte. So soluble ionic compounds, 100%, if it's soluble, it's going to all form ions. It's going to fully dissociate. That would be a strong electrolyte. Soluble covalent compounds, they do not dissociate. No ions are going to be formed, so it would be a non-electrolyte. Strong acids, 100% ionize, so it's going to form 100% ions. It would be a strong electrolyte. But a weak acid only forms only a little bit of it ionizes, so that would be a weak electrolyte. Strong bases, all of it's going to ionize, so that's going to form 100% ions. That would be strong electrolyte. Weak bases form a few ions. That would be a weak electrolyte. And then insoluble ionic compounds, they don't form solutions, so therefore they're non-electrolytes. So it's important that you can identify, looking at a chemical formula, is it an ionic, covalent, strong acid, or weak acid from its chemical formula? Really, the bases are mostly going to be strong bases, are also ionic. And then make sure you understand why each type of compound is either a strong, weak, or non-electrolyte based off of, does it form ions or does it not form ions?